Linear gradient is the last of our common patterns that we're going to take a look at. This one's really useful if you're dealing, say, with some projections to go out in the future, and you're dealing with individual sub-series within your cash flows that you know are going to have certain kinds of percentage change. So it could be something along the lines of you expect your direct labor costs to go up by 2% a year, you expect your indirect labor costs to go up by 7% a year, you expect fuel costs to go up by 12% a year, and essentially what it does is it allows you to go ahead and basically make some estimates for a first year, put in some assumptions that you're going to make about the rate that they're going to increase over time, and then combine these sequences out in order to find the present value of cash flows. Now, a quick description of what we're looking at here for a geometric gradient is you always start with some value. Oop. And so we'll go ahead and put time coming out this way. And this first value is that a sub 1 value that we have over here that's part of the equation that you should take a look at. This could be something like 10. It could be something like 20. It's not like the linear gradient where it has to start at 0. And after that, that lowercase g indicates the percentage change that's going to take place each period. So if this object right here is, say, a 10, an interesting kind of geometric gradient would be if it cut itself in half every single time period. So the next time period it went down to 5, and then 2.5, and then 1.25. And this would be a geometric gradient with this growth rate of negative 50%. So again, that's a nice, easy one you can take a look at. It could also do things like double every single time period. So you could conceivably have something that starts at 1 in time period 1, which is what we're looking at right here. The next period it doubles itself up to 2, and then it doubles itself up again to 4, and then it doubles itself again to 8, and so on. And this is one that has a lowercase g of 100%. So again, you can have any one of these particular patterns right here, but that's an example of what we're using for our geometric gradients. Now, an explanation of the factor notation that goes along with something like this. And so I'll erase this little component right up here, just to make sure that you're reading off right. So for our geometric gradient, say that we're looking for the present worth. What we're doing is starting with the known value, which is in time period 1, so that's a sub 1 there. Reading off, we're looking for p. Remember, if we're looking for the future value, there'll be an f there. Given that we know, and what we have right here to the right of the slash mark is the known value in p sub 1. So remember that these two things match with each other. In this case that we have right down here, that would be a 1. Then what we have to worry about is whatever the interest rate is, so whatever your problem says, and then we're looking at what that growth rate is. So in this case we could put 100% there, and we could replace our a sub 1 right there with the 1 that we start with. What we'd have is the present worth of a geometric gradient series that starts at time period 1, has an interest rate, whatever it may be in our problem, and a growth rate of 100% per period. Basic explanation. There is, however, this tricky little piece with the geometric gradient, and that has to do with there being two forms, this one and this one, depending upon if the interest rate and the growth rate are different from each other, and that's what that top one is supposed to be, or if they're the same, that's what the bottom one is supposed to be. The problem shows up if you look down here in the denominator. When I and g are equal to each other, this turns itself into a 0 and the whole thing's undefined, which is bad, and that's when this simpler form comes into play right here. So there's your explanation of the geometric gradient. Thank you.